So let's start by having so we have the sample, and we know what is the sample space, right? Then we learn about events. Which are subspace of your sample space. Then we learn about counting outcomes. So if we want to know how many outcomes we have in an event or in your sample space, we know how to do that already. Now we can relate this to your sample space. So you can count for both, for your events and for your sample space. Also, we know how to get the probability of an event. And you need to know how many outcomes you're going to have in your event and also in your sample space in order to get the probability. And this is also tied with events. And finally, what we're going to be learning today is random variables. So for random variables, you need to know probability, and also you need to know what is a sample. And basically what we're going to do is we're going to assign numbers or values to our sample space based on probability. Okay, so this basically shows you why are we going in this order, and we're going to cover this part today. Okay, so random variables and probability distribution. This is material that is in your textbook in chapter 3, using part of the material from your textbook and also from the other references. And essentially what we're going to cover is what is the concept of a random variable, what are discrete probability distributions. Remember in our first lecture that I was basically saying what every time, remember the difference between discrete and continuous. Now you're going to see why that is important. So we're going to discuss discrete probability distribution and continuous probability distributions. And finally, joint probability distribution. So let's start by discussing the concept of a random variable. So statistics, and I think this is something that you saw also at the beginning of the semester, is concerned with making inferences about population and population characteristics. Okay? So, for example, the testing of a number of electronic components is an example of a statistical experiment. So remember, what we are trying to do in this course is basically summarizing this diagram. We want to make deductive reasoning about your population, about every item that you have in your process. You're going to use probability to basically show how to get a sample. And you know what a sample is already. And using the sample, we're going to use statistics to make inference about our population. Okay, so keep this in mind. So we start by saying what statistics is doing. It's concerned by amount making inferences about your sample. So you can make deductions or comments about your population. But it is often important for you to allocate a numerical description to an outcome. So if you remember for the head and tail experiment, we were just saying head, tail, tail, but we were not assigning any value to those outcomes in your sample space. Now with random variables, we're going to assign values to each outcome in your sample space. Okay? So the sample space giving a detailed description of each possible outcome. When 3 electronic components are tested, can be written as this. And this is also an example that we saw. So basically what this says is, if you take 3 components, you can have 3 of them non-defective, 2 of them non-defective, and 1 defective, and so on. So when you perform such type of experiment, what you're trying to find out is how many defective components would you see in your experiment, right? So each point in the sample space will be assigned a numerical value. So if you're counting the number of defectives every time you get a sample, then you can assign a number to each outcome in your sample space. So for this specific case, you can have 1 defective, 0 defective, 2 defective, and a maximum of 3 defective, because you are taking only 3 at a time. Okay? So these values are random values assumed by the random variable, and then we're going to assign a name to that random variable. We're going to use x. Okay? So for example, if we look at that sample space, the one that is n, n, d, and so on, if you were to assign a value to each outcome, starting by the first one, and you're counting the number of defectives, what would be the value of the first one? 0, 1, 1, 1, 2, 2, 2, and 3. There you go. That's your random variable. Random variable basically is going to have 3 values, 0, 1, 2, and 3. And each outcome is going to have a different probability. Anyone can tell me what's the probability of having a 2? 3/8. Correct. So for that experiment, you are having a probability of 3/8 to get 2 defectives. That makes sense? Okay? So that's the type of things that that's where we are moving to. Okay? So with random variables, we can assign values to each outcome of your sample space. Then with those values, you can construct a probability distribution that is going to tell you, for those values, what is the probability of seeing that specific outcome in your sample space. Okay? So that's why random variables are important. Okay, so a random variable is a function that associates a real number with each element in the sample space. Okay? So in order to have a notation for this random variable, we shall use a capital letter, say X, capital letter, to denote a random variable, and its corresponding small letter, say small x, in this case for one of its values. So the random variable can have values from 0 to 3. That is denoted by the capital X, but 1 will be denoted by itself by the small x. Okay? So we have another example here. Let's say we have 2 balls drawn in succession without replacement from an OR, containing 4 red balls and 3 black balls. So the possible outcome and the values of y, of the random variable y, capital Y, is the number of red balls. So let's assign those values here. So if you have the first outcome are 2 reds, this is 2. If you have 1 red, this is 1. 1 red, this is 1. No red, this is 0. And this is the same thing we did for the defective and non-defective example. We know what's the sample space. You're taking 2 balls at a time. And these are the possible combinations that you can have. You can assign values based on your random variable. In this case, our random variable is y, which is the number of red balls. You can have another random variable, let's say W, which is the number of black balls, then you can have different values here for that random variable. Okay? So, definition of a random variable, a function that associates the real number which is element of the sample space. Okay, so let's say we have another example here. A stockroom clerk returns 3 safety helmets at a random to 3 steel mill employees who had previously checked them. And we have 3 employees, Smith, Jones, and Brown, in that order. So we have Smith, Jones, and Brown. And they received the helmets in that order. List the sample points for the possible orders of returning the helmets and find the value of M of the random variable M that represents the number of correct matches. Okay, so we can start with the order that was given. So we have going to use S, J, and B. And I'm going to list the possible combinations for returning those helmets. So you're going to have 6 sample points. Let's put S, B, and J. J, S, B. Okay, and what we're trying to find out for this value is the number of matches. So we know the original order. So for that original order, we're going to have 3 matches. For the next one, how many? Only 1, right? S. For the next one, 1, which is J. For the next one, 1, and then 2 zeros. Okay? Very simple. Just assigning value to your outcomes in your sample space based on your random values. Questions? So we did 3 different examples. We are doing the same thing. But again, the value that you're going to assign to each outcome is going to depend on your definition of your random variable. There's no only one random variable for each problem. So you're going to have to understand what the random variable is asking you to do in order to get the right outcome value. Questions? Okay. We're going to have another random variable that is very important. This one is used very often. So in order to introduce that random variable, I'm just going to use this example to consider the simple condition in which components are arriving from the production line, and they are stipulated to be defective or non-defective. Define the random variable x, y. So what are the possible values for these random variable? Exactly. We can define that random variable using numbers by just assigning 0 and 1. 0 to denote that the component is defective. I'm sorry, 1 if the component is defective, 0 if the component is not defective. This type of variable, it's a binary variable. This random variable for which we are using 0 and 1 to define the values is called a Bernoulli random variable. Okay, so remember that name, a Bernoulli random variable. So you're going to have 0 and 1s, just 2 values to define a random variable. Okay, so physicians use sample plans to either accept or reject batches of lots of materials. So suppose one of these sampling plans involves sampling independently 10 items from a lot of 100 items, in which 12 are defective. If you were to define a random variable, let's say the number of defective in the sample of 10, how many values that random variable would have? Number of defective in your sample of 10. How many values would you have? So you're choosing 10 from your sample. From those 10, how many defectives can you have? 10. You can have 0, you can have 1, you can have 2, up to 10, right? So your random variable needs to capture all the values that you can have from that experiment, which is the number of defective. So let me write that down. Let x be the random variable defined as the number of defectives in the sample of 10. So what are the values for this random variable? X can have values from 0 up to 10. Because you can get 10 items, and from those, none of them are defective, so the value for your random variable is 0. You get 10 and 5 of them are defective, the random variable value is 5. Okay, is that clear? Questions? Remember, we went from defining the outcomes in the sample space. Now we want to assign values to those outcomes in the sample space based on the definition of the random variable. Okay, another example. Suppose a sampling plan involves sampling items from a process until a defective is observed. The evaluation... Yeah.
We understand that there would be 12 defective items in 10. They obviously all be defective.
You only have 12 out of the 100.
Right, but they all can be, as we put 10,
yeah.
They all be detected with probabilities. If it's chosen at random, you're not going to choose all defective items. What's the point of the sample?
Yes, that's correct. So the only thing that we're doing here, we're not assigning probabilities to those events yet. The only thing that we're defining here are the values that that random variable can get.
Okay, so you're just saying it's feasible.
Is feasible. All of them are feasible. Yeah. So even though you have 12 defective, if you are lucky, you can get all of them if you pick 10. Or unlucky, because in this case are defective. Okay? So now from a different point of view, again, we are defining a different random variable. Now we're supposed that a sampling plan involves sampling items until you get a defective. So the evaluation of the process will depend on how many consecutive items are observed. So for this one, let's say you sample one item and that one is defective. What will be the value of the random variable? 1. Because you got your defective on your first item. Now, if the sample is, say, non-defective and defective, what will be the value of X? 2, because it took you 2 items to get 1 defective. And you can repeat that. If we go back to these numbers, you can repeat that until 80, 88. So you can get until 89 until you find the first defective. So your random variable can have values from 0 to 89. Okay, because if you get all of them not defective, you know that all of them are defective. The last unit that you will get without being defective will be the 88. So the 89 has to be defective. Okay, so and so on. Okay, questions? I think we have one more example. Let x be the random variable defined by the waiting time in hours between successive speeders spot by a radar unit. How can you define a random variable for that? So now we're not looking at discrete events. You cannot count the waiting time. It's a continuous line. You can have 1 hour, 36 minutes, I don't know how many seconds. So this is a continuous random variable. So if you want to define a random variable that is continuous, you're going to have to use a range. You're going to have to use symbols like greater than, less than, and so on. So for this case, the random variable x takes on all values x for which x can be greater or equal to 0. So your waiting time can go from 0, no waiting, up to days, years, I don't know, what else, okay? So we define that random variable using a greater than or equal to 0 value. Okay? So we're going to go back to what I just explained to you at the beginning of the class. So now we're going to define sample space for continuous, sample space for discrete. And you see why that is important, at least for defining a random variable. Now, in terms of the sample space, if a sample space contains a finite number of possibilities or an unending sequence with as many elements as there are whole numbers, that is called a discrete sample space. So you can count them, you can list them, and so on. Now, if the sample space contains an infinite number of possibilities equal to the number of points on a line segment, that is called a continuous sample space. Continuous. Continuous random variable. Okay, two very important definitions. So a random variable is called discrete random variable if its set of possible outcomes is countable. So it represents count data. Okay, for example, the number of defectives in the sample of K items, or the number of highways fatalities per year in a given state. That's our type of things that you can count. Now, when a random variable can take on values on a continuous scale, it is called a continuous random variable, and it represents measured data, all possible heights, weight, temperature, distance, life periods, whereas discrete random variable. Is that clear? It's very important for you to understand the difference. Count, measure, continuous, discrete.
So which one is really a range? 0? Yeah.
Okay. Yeah.
So discrete, basically there's no range.
If you count something,
Right.
that can be described as a discrete random variable.
Look, then,
It will be,
no, no.
it can be infinite, but you can count, still count. They just, in most of the cases, you're gonna have an amount of value, but it also can go to infinite. But the important difference is that you can count those down. So let's look at this problem. I'm going to give you 2 minutes to answer these questions to decide whether a discrete or continuous random variable is the best model for each of the following variables. You have several cases, and I want you to identify if it is continuous or discrete random variable. Okay? So 2 minutes. Can you see it? Okay, let me know when you're done.
What is injection molding?
Which letter? F. Yes, it's something in which you're trying to build a car, for example, and you can have that mold, and you can put some material inside of it.
And I think it was like a mold, and you can actually work with injection on plastic.
Yeah.
Oh. Like let's see, like a.
Okay, let's discuss the problem. So for letter 8, the time until a projectile returns to air. So continuous or discrete? Continuous. The number of times a transistor is a computer memory changes state in one operation. Correct. The volume of gasoline that is lost to evaporation during the filling of the gas tank. Correct. The outside diameter of a machine shaft.
Discrete.
It depends on the scale. If you can measure it down to the atom thickness. I guess that would be
Yes.
discrete.
That's why it's going to be continuous. So if we go measure data belongs to the continuous. The number of cracks, discrete, correct. The weight of an injection mold, plastic. The number of molecules, correct. The concentration of output from a reactor, continuous. And the current in an electronic circuit, continuous. Questions? Okay. So now we know about continuous random variables and discrete random variables, right? Now, let's take that to the next level. Now we're going to start dealing with probability distributions. Okay, so we know probability. Now we're going to have this term, discrete, and we're going to have this term, and we're going to have discrete probability distributions. Okay? So a discrete random variable assumes each of its values with a certain probability. Remember the example, non-defective, defective? We're able to assign the probability to each of the outcomes. Now, we represent all the probabilities of a random variable x by a formula. Such a formula would be necessary be a function of the numerical values x that we shall denote by f of x, d of x, r of x. You can choose one of the three, and so forth. So we're going to have a function that is a formula that is going to define the numerical values for this random variable. So the set of ordered pairs, let's say the value and the value of that value in the formula, or the output of that value, is called the probability function, or the probability mass function, or a probability distribution. Okay, so you can use this term for discrete and continuous. You can use this term for discrete and continuous probabilities, but this one, specifically the mass function, belongs only to discrete probability distributions. Okay? And I'm putting a picture here just to remind you that for discrete, there's things that you can count. Okay, so this is a more formal definition. It's coming from your textbook. So the set of ordered pairs, x and f of x, is a probability function, probability mass function of probability distribution of the discrete random variable x if for each possible outcome, x, we have these three conditions satisfied. So there's three conditions. The value evaluated in the function will always give you a value greater or equal to 0. Could not be a negative value. Second, the summation of the values of all the outcomes needs to be equal to 1. And why is that? Why? Yes, correct. The probability or the summation of the probability needs to be equal to 1. If you have a summation that is greater than 1, you're doing something wrong. Okay, so that's something that you can use for verification purposes. And for a discrete random variable, if you look at the probability of the random variable x being equal to a certain value, let's say x equals 0, that value is given by evaluating the function in that value. Okay, so the probability of x equals 0, and you have a function that is x equals 2, then you can you can put 0 in x squared, and the probability will be equal to 0. Okay, so again, it needs to satisfy these three conditions. Let's look at this problem. A shipment of 20 similar laptop computers to a retail outlet contains 3 that are defective. If a school makes a random purchase of 2 of these computers, find the probability distribution for the number of defectives. Okay, so let's define the random variable. What will be the random variable in this case? Number of defectives, correct. So x be a random variable whose values x are the possible number of defective computers purchased by the school. Okay, so that's your random variable. And what are the values that this random variable can take? 0, 1, and 2. Everybody got that? And why is that? Because you can only have 0 defective, 1 defective, or 2 defective. Okay, so x, small x, can only take the values 0, 1, and 2. Okay, so let's find the probabilities distribution for the number of defectives. So in order to get that probability distribution, we need to find the probability of getting 0, 1, or 2. Okay, so let's start by finding the probability of x equals 0. Any ideas on how to get that based on the material from our second lecture? So now we need to find the number of outcomes divided by the total number of outcomes that can happen in this experiment. Okay? And what are the things that can happen? You pick 3 and none of them are defective. That's the first case, non-defective, 0 defective. Okay, so let me write this down. So by theorem 2.6, we can use this to find the number of combinations of n distinct objects taken are at the time. So our probability for x equals 0 is defined by the number of outcomes by selecting 3 and none of them are defective. We're starting with x equals 0. Oh, so you're using, yeah, well, wait. So from the 3 you select 0. Then you need to multiply that 17 out of the 2. And that will give you the total of combinations for selecting 2. And none of them are defective. And this is 20 over 2, which is the total number of combinations. This will give you 68 over 95. Now for x equals 1, so this is for x equals 0. The probability of x equals 1, that will be equal to, from the 3 you select 1 that is defective, and 17 you select 1 that is not defective, over 22. And that will be equal to 51 over 190. And for the probability of x equals 2, you're going to have, from the 3 you select 2 Then for 17, you select 0 that are non-defective, and the total, and that will give you 3 over 190. And that defines the probability for the events that you can have for that particular random variable. Now, if you sum these three probabilities, what will be the total? 1, correct, because the summation of the probability has to be equal to 1 based on the conditions. Okay, now the question is telling you find the probability distribution for the number of defectives. So we have the values. This is f of 2, f of 1, and f of 0. So we can write the table that basically tells you the distribution. So for x with values 0, 1, and 2, we have f of x (68 over 95, 51 over 190, and 3 over 190. And this is our probability distribution. So the probability for getting 0 will be this one, probability of getting 1 will be this one, and the probability of getting 3 is this one. Not so simple, right? So now you see that things are getting more complicated. Okay, so if you understand this, then going to this thing will be easier. But if you're still struggling with this part, then getting to this point will be a different thing. So that's why I want you to practice and go over the material that we finished today at the beginning, because we're going to be using that a lot. Okay, so this is the answer for the problem. Okay, let's look at the next problem. Can I go to the next slide? Yes? Okay. Okay, we have if a car agency sells 50% of its inventory of a certain foreign car equipped with side airbags, find a formula for the probability distribution of the number of cars with side airbags among the next 4 cars sold by the agency. Okay, so I'm going to start by just listing the sample space. So let's say A is the airbag and N is no airbag. And we are looking at the next 4 cars that we are going to sell. Okay, and we can basically list the outcomes for each car, and we can list the sample space. So we can start our sample space saying that none of them have airbags, one of them have airbags, and so on until you get to all of them having airbags. And you're going to have a total of 16 outcomes. So this is from the second lecture. Output is the sample space, right? So we have 16 outcomes. Problem is also telling you that there's a 50% of that each car will be with airbags or no airbags. So you can basically say that each outcome we have a 50% probability of being non-airbag, which is 1 over 2. So if you multiply this 1 over 2, 1 over 2, and 1 over 2, this is going to give you 1 over 16. So each outcome will have a probability of 1 over 16, which is the same as saying that 1 over 16, which is the total of outcomes. Okay, so each outcome has a probability of 1 over 16. So what we can do is to define the function. We know what's going to be the denominator. It's going to be 1 over 16. And we can use theorem 2.6 to define the number that we are going to be selecting, where x can go from 0 to 4. And that will define our function. This is the same as saying 4x divided by 60. Okay, and that's the expression. Questions? Okay, so what I'm planning on doing is I'll give you some practice problem again. Today I'm going to post some new homework. So please take a look at those problems and ask me questions. Okay, don't wait until next week, until the day of the exam to ask questions. Okay, so that's two problems. Basically what we are doing is defining the functions for the probability distribution. Now, let's refer back to this slide. Anyone remember this slide from our first lecture? So far we have been defining probabilities for events x equals 1, x equals 2, x equals 3, and so on. But we can also define the probabilities that are cumulative. And at the beginning of the class, I showed you how to construct an histogram for cumulative values, and this was the example that I was using. Okay, so you're going to see that this is going to become handy now that we're going to cover the next topic. So what we did here was count how many units were less than 5, how many units were less than 9, how many units were less than 13. And we knew at that point, or I explained it to you, that when we look at the units that are less than 13, that also includes the units that are less than 9. Okay, so we can say that these 13 includes these 3 units, because these 3 units are also less than 13. Same thing happens for these 27, when we include this unit and this unit, because these are also less than 17. So what we're doing is a cumulative distribution of numbers. Okay? So there are many problems when we might wish to compute the probability that the observed value of the random variable will be less than or equal to some real number. Less than or equal to some real number. So if I go back to the example, really quick, if I tell you how many units are less than or equal to 17, you can tell me easily 27. Okay? So writing that probability can express that with the capital F. So we're using small f to describe the function of the probability distribution. Now we're going to use capital F to denote the cumulative distribution. And it's basically the probability of this random variable be less than or equal to a number. In that case, less than or equal to 27. Okay? For every real number, we define f of x to be the cumulative distribution function of the random variable x. Okay? So, formal definition from your textbook, cumulative distribution function f of x of a discrete random variable x will probability distribution f of x is the summation, everybody recognize this symbol? Summation from a value up to x of all the values evaluated in that function. You're going to see that in an example, okay? But you're going to sum all the probabilities up to x, and that will give you the cumulative distribution. Okay, so going back to this example, this is the same example we discussed earlier today. I'm just going to type the solutions here, right? This is something that you already have. So we have S, J, B. This is 3. S, B, J, 1. B, J, S, 1. J, S, B, 1. J, 0. B, S, J, 0. Okay, so here we were counting the number of times that we were matching the same person. Now the problem is asking you find the cumulative distribution for value 2. So we need to add the probabilities from 0 to 2 and find that value. So what we do, we want to find f of 2, and that is equal to, based on our definition, x less than or equal to x. And this, in this case, our random variable is m. So m be less than or equal to what? 2. Okay? So this is the generic case. This is the case for this problem. Okay, so what are you going to do? You're going to sum the probability of, this is equal to the probability of 0 plus the probability of 1 plus the probability of 2. What is the probability of 1? Oh, actually, let me change this. I think this is more confusing. Let me change this. Is x equals 0 plus the probability of x equals 1 plus the probability of x equal to, I'm sorry, it should be m. Okay, can you tell me what are those probabilities? 0, 2 over 6, right? 1/3. M equals 1. And m equals 2, 0. So this is equal to 5 over 6. Okay? That's the cumulative. You sum this amount, and this amount because you're satisfying the constraint less than or equal to 2. So those values are 0, 1, and 2. 0, 1, there's no 2. Questions? Okay, I'm gonna stop here. Please go back and read the slides, ask questions. I'm gonna be in my office this afternoon, Friday all day. And homework, you can do tonight. Take a look at the homework. We're gonna have a week.
Yeah, posting all the. Again.
You said the next homework will be due in
Oh, sign in. That's it. I'll sit in the back. When it got to the back, I moved up to the front.
Just 1 second.
Yeah.